Hello and welcome everyone. In this day 39 learning, we are going to be looking at tries, TSTs and suffix trees, right? So tries is a data structure that we use specifically for working with strings. So tries, let's say we have a string like uh, cat, car, cart, dog, and door. So these can be simply represented like a tree, like a C, let's say a root node, and D. Again, look at the way that characters are organized. These are like a BST but operating on characters of a string. C, A, and R and T. So this is like a int, and and D O R D O G. And here we get D O R and D O G, right? So we have three words like cart and car, cart, and dog, right? Okay, so the last thing that we have here is do, and this would be and this would be r. So this would be the end, and this would be DOOR. So consider these two separate things. One is DOG and DOR. O again has a child node of O and R, right? So to form door, and DOG and cart and car and DOR. So that's a simple try here. There might be multiple operations in a try, like search, insert, search, insert, search. Starts with display all the words, so on. So yeah, display, right? So so a simple try node would look like something like this. So children is equals to a map, and also would have a flag is end, which would be initially at false. So this would be a simple try node, right? So the entire try block will have all of these functions that we talked about. So let's look at the insert method and few easy methods that we can think about. Let's say we give a word to be inserted. So first, so we take the current node, which is equals to root node, uh, from the try class, which would have a constructor and a root node. And next, for each character in word, we check if character not in root character is not in root or the current value, current node, then we simply add or set the character, and we continue to do this. So this way all of the characters would be appended, like, and we also need to set the current character is equals to current dot children dot get ch, right? So this is like a linked node traversal where we set the current node to the next node, and then we start again adding the next set of words in this for loop, right? So that way we also complete adding to the uh, root node, and once all of these words are iterated, then we start saying uh, current dot, after the for loop we say is end is equals to true. So this would be the end of the word. Okay. So similarly, there can be search method also, which works in a similar direction. I will not explain more on this. We will quickly switch to JSPin and let's look at how the code implementation is done. Okay, here in JSPin, I have a try node here and a simple constructor, which is like a definition of the current root node or the starting node. And once we insert a word, we start off with the root node, then we start adding the uh, characters of the word like a new try node, and we iterate through the entire word, and we also need to start off with the newly added character, right, and assign it to the character so that the next character would consecutively take the other set of characters as a linked list as a try node, right? And at the end of the for loop, we have is end of word is equals to true. That's the insert function that we looked at. So there are other methods like search, starts with, and display, which is pretty much easy to understand. I would not take time explaining that. I would paste this code in the GitHub and share the same link in the video description, which you can go through. And if any doubts, please do post them in the comment section. So that would be an interesting discussion forum. So next would be TST or ternary search trees, right? So in trees, we saw that it is like a prefix based, but there is also a suffix tree which starts off with a suffix character, and there are different use cases with trees and suffix trees and also ternary search trees, right? So understanding the concept would give us idea on where to use them. So yeah, let's start discussing on TSTs. So in case of ternary search trees, so let's say we have these set of words which we looked at: cat, car, and dog. So we can say these two as having a common word and R and T. So yeah, this would be a simple ternary data structure. So in this TST, the root TST node would look like having left, middle, and right. right, if the character we are looking for is greater than, we go right. If it's equal to the current character, then we go middle. Else, if we find a character less, then we go to the left side, right? So yeah, and also few other properties like end of word, and also a character. So these three are something that is different as compared to the uh, trees or the prefix trees where we only had left and right values, right? So yeah, let's there are few methods like insert, search, display in TST as well, but we will look at the insert method in TST. And the easiest way to think about this is, let's say we have car, cat, and cat. So let's say these three set of words we want to insert. So let's say we take the first word. So we start off with this dot root and the word, and we start off with index 0. So ins record, let this be a recursive implementation. So let's say if uh, so the insert record function, let's say this be a node, word, and an index. So and we take each character of the word at index, and we check if node is null, node is equals to null. Then we create a new uh, tst node, new node, and we start off with a character which is C, right? And since this is a new node, we simply can say we can simply keep inserting records with node.middle, and this dot insert record taking node.middle, word, and index plus one, right? So that's the whole idea. So let's say once we are inserting new word like a car, we are fine. We can insert all of them to the node.middle. In order to make this recursive function more compatible, so the way that we modify it is, let's say if a character is less than node character, then we can insert it to the left. Like for example, car, we inserted all the values to the middle. Now it's time to check cat, right? This last word, node dot left. Else, if this character is greater than t, then we insert it to the right, right? Node dot right. Else, we firstly check if index is equals to word dot length, which should signify it as the end of the word, then we make sure this is end word and we change this to true, right? Else we can have our logic where we insert all the elements to the middle, right? Like a new word insertion. So on, right? So hope you understood the logic. Let's say we first time we insert, everything will take up this logic where it's neither equal to uh, neither less than, neither greater than, but uh, not even equal to the length of the word. So we just go insert into the middle. Once we start having more characters, like c c is equal to the word, and we simply keep checking if there is, if it's not a null value, then we simply continue and we check if it's again equal to character, then we simply proceed with it. And if it's uh, r and t, then we check t is greater than r, so we insert new value of t by moving to the right with a new tst node, right? So that's the whole idea. Hope you understood the logic. Let me switch to JSPin and let's quickly understand the code, and we should be able to complete TST. Okay, so here we have TST node. So as we said, we have a character left, middle, and right and end of the word. So this is a recursive call. We start off with a root and we send the word with a starting index of 0 and a recursive call uh, to left or right to create new nodes. If there are any, else we simply keep checking if there is middle of the node, and so on, right? If it's a new word, then it keeps getting added to the middle, else it gets moved to the left and right position of it, right? So that's the whole idea. uh, yeah, so I will not explain more on the search or the starts with or the other display or search. So I will leave the code section analysis, uh, and if there are any doubts or thoughts or comments, please do post them in the comment section, right? The last part is suffix trees. Similar to the trees where we looked at this tree, so we start off with a word and we start forming from the first character. This would be a little mirroring or an opposite way where we start off with the ending character and then start forming set of characters, right? So yeah, let's switch to drawing board and let's quickly understand suffix trees. Okay, let's take an example of the word Google. So let's say we have a word Google, 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 right? So let's say we start off at E E L G L E O G L E O O G L E, and again G O O G L E, right? So the way that we form a, this is again should be converted to a tree, like we start off with E, and let's say we have like E and L and G and O. O is repeated, so and G is also repeated. So this starts off at a character, the ending character. Let's say we have 0, 1, 2, 3, 4, 5. So this starts off at 5, comma 5, and L starts at 4, comma 5, 5. G starts at 3, comma, and this one starts at 2, comma 5, right? 2 and ends all the way. Okay, so under E, this is the only string. So under L, we also have E. So this is ELE, and under G we have GLL, and L and E, and again we have O, O, G, L, E, right? So this one, and so this the end. So this is the end, and this would be the end for this one. This one is this character, GLE, right? So while LE is this character here, and GLE. So others can also be mapped out like O, G, L, E, and OOGLE. So OOGLE. So yeah, little tight in space here, so I'll not draw out more things. But yeah, I guess you get the point here, right? And this one is here. So all of these we have drawn. So let me just take this here. So let's say we had O, E, this is the end, and L and E, L and E, and G, L, E, G, O, O, G, L, G, L, E, O, G, L, E, O, G, L, E, right? So yeah, these are the set of words. So now let's say we can still compress it, like so we can still compress it, like we know that E, L, E, G, L, E, and O, O, G, L, E. This is all under a root node, and this one S, G, L, E, and O, G, L, E. So this is fifth character. So G, O, O, G, L, E. G is 0, 1, 2, 3, 4, 5, 4, comma 5. This would be 4, comma 5, right? And here would be 3 comma 3, and this would be 4 comma 5 and 1 comma 5, and the same goes here, which is this is 2 comma 2, and this is 2 comma 5, this is 3 comma 5. So this is the way that this goes, right? But we will look at a simple implementation of how this tree is formed. So this is like again a simple tree, but only thing is we are having to map the characters from the last. So that's the whole difference in suffix tree. Let's look at the code implementation. It should be very similar to the normal tree, except the suffix tree having to reverse the characters at each point, right? Okay, so suffix tree has a similar kind of tree node implementation as child with this of a map type, and a suffix tree with insert method, all similar to try node, just that starts with build from text that takes in like suffixes or portions of a string with the slice method starting from I. So that's the whole difference in implementation here. This is a simple implementation. There are implementation which also can help us identify the indexes, so such things, but I will not add a lot of complexity into suffix tree node. This is just a basic understanding, and I will stop this video for now. I will also attach all of this code section in the GitHub link with this video description. Please do post any comments. Happy to respond there. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.